Alright, hit the button. So we should be somewhat live-ish, maybe. And where's the little buttons I have to hit over here? They don't appear to be here. That's very strange. So I guess the chat is already popped out. Well, I'll restore it. And then, yeah, now it's there. Okay. Very strange. So, something new. Feature, fun thing happening. Yeah. All right. Gee, it's really kind of annoying. Anyway, doesn't really matter. Mostly just annoys me, right? Yes. Okay. So we'll play some momentum videos. We'll play some. We'll just see how far we go, where we go. There really isn't anything, unfortunately. There's nothing describing the specific circumstance. Okay, so you can't find the exact circumstance, and you sort of need the exact one to make it more obvious or clear. So I have here, okay, a little suggestion regarding the video Ian did demonstrating what I guess you could argue was a failed gun. So, let's see, maybe I can move that. I don't know whether I should or not, but that's the wrong thing. That's what I want, is this one. Yeah, that's the one I want. Okay, I can't move that, so I can move this over here. Alright, close enough. Alright, so this is just, and I don't like the glare. There's always something to complain about. You should maybe tie the springs down. I didn't, thinking about it, it's not ideal to have a bunch of springs in series. So you probably should just take some fishing line and tie them together, just so they can't move independently and push each other away from what's happening. So they're kind of forced to stick, and you might as well just tie them to the base also. That would be a suggestion. This marker really isn't the one I'm supposed to be using. So anyway, there's always something. Try this one. It also smells poorly. Alright. So the simple experiment is you have a spring, you compress it the same amount each time. So you compress it to a certain amount. Then you put a 2 mass on it, and then you do a simple experiment where you put a 1 mass on it. Alright, and the idea is, like a gun shooting a bullet, momentum is conserved, and you get, whatever this velocity is. Let's say it's 100. This velocity will be 50, half that. Alright, yeah, that was a mistake. This is going to be 100, and this would be 50. Okay, so 2-to-1 relationship between the mass and the velocity, just the inverse. And this would be a reasonable expectation. And if you were shooting it into gravity, your expectation, say if these were bullets of different masses, the one bullet would travel this far and no farther. And the one going twice as fast will go through the gravity twice as fast. It will go 4 times the height. But it'll only take twice the time. It'll only have twice the weight, and it will only what's the other one? Yeah, there's another one. I can't remember the other one. Anyway, the time one is the big one. That's the important one. And that's just what your expectations are. So he did the experiment, and this is as far as the half mass went. Clearly, it wasn't going twice the speed. It was only going, say, 1.4, which would be something like 1.4 of 50. So 0.4 of 50 would be 20, so it's like it's going 70 or something. Alright, so it's short of what it needed as a velocity to get to where it should have gone. And you have to explain that it's a non-conservation of momentum. So the analogy would be you have a gun, alright, and somehow you shoot the gun, and instead of conserving momentum, Okay, so when the gun conserves momentum, the bullet leaves very fast, okay, and the gun leaves very slow. So you have a big differential. The kinetic energy gets huge in terms of the differential of 2,000 joules going this way and only 2 joules going this way. Now, he's saying this gun, okay, completely fails to conserve the momentum. That is the, you could say the one atom going 2,000 miles an hour versus the 2,000 atoms going 1 mile an hour. It doesn't do what the gun does. That somehow it conserves the kinetic energy, and so the bullet leaves pathetically slowly by comparison. And you don't have this huge differential because you don't conserve the momentum. So I'm just saying it's a basic rule of physics that yes, you have to conserve the momentum. The energy has to go somewhere. So if you're going to say you're not going to conserve it, then you have to make some explanation stating that, well, the gun was going 900 miles an hour this way. Okay, so the gun was going so fast in this direction that the explosion couldn't be an explosion anymore in that direction. Something, so what's the weakness here? The ground failed? Well, it's unlikely that that could be the explanation because it's the same pressure here, and if the ground's going to fail, that is if the ground's going to move and absorb the energy, right? I mean, if I'm moving away from somebody and I punch them, my punch is diminished in its strength by how much I'm moving away. So if this object, the ground, is moving, well, that failure would happen with both objects because it's the same technical pressure on the spring. So there's no reason to think the loss of the energy was through the ground. So you have to come up with some other explanation for where to go. Somehow the spring failed, I don't know. Can't really think. I mean, obviously it would be nice to tie the springs together and have them firmly seated on the ground. Maybe that'll help. But that really doesn't seem like the explanation. So all you're really left with is the method you use to release the objects. And somehow that method doesn't allow the twice the velocity to happen because it interrupts the process of the launch. The highest pressure point is dragged up over time, and you're allowing the object to move, and then you're stopping it, and then you're moving it, and then stopping it, and moving it, and stopping it, and you're absorbing the strongest pressure in the spring is being absorbed by a bunch of counter forces of friction, because you're not releasing the object quickly enough. So that seems a likely candidate. That's one I'll vote for, okay, if I'm if I'm required to vote. But something has to be an explanation. I mean, if you're going to say the gun doesn't work, you've invented a gun that doesn't shoot bullets correctly, then you have to explain why your gun doesn't shoot bullets correctly. You can't just say it doesn't. There's some reason why it's not working. So they don't think they have to explain why it isn't working. Okay, they think it's all the guns don't work. So they're telling you basically that guns working is an illusion, a fakery of science. They've been lying to you that guns do this, that bullets fly out at this high velocity and guns fly off at slow velocities and momentum is conserved. They've been lying to you because kinetic energy is conserved, and that's what he's proving. Momentum isn't, kinetic energy is. So in that context, we'll play the Professor Lewin video. And such. Again, I mean, I did play it years ago. We'll start somewhere around here. I mean, some of this was kind of boring, where he's just talking shit. Yeah. And there's, unfortunately, we're going to have to endure some commercials, which is really kind of tacky, frankly. I mean, I've said it before, but it's really kind of pathetic that a MIT college professor would have to, squirm for a few dollars. I mean, commercials. I mean, frankly, he could have, instead of giving this, signing some contract with some company that gives him a bulk payment, he could have just put a thing on the video saying, please donate to remove commercials. You know, so my science isn't polluted by this crap. You know, but no. The liberal MIT professor instead chose to, you know, buy into the ragged capitalist system and exploit his poor viewers. But whatever, that's my commentary. Just bad form, frankly. I'm sure he could have raised the money from his devotees to keep his science clean. All right.
External forces on the system. When they collide, you better believe it that there are internal forces. You better believe that there is glue. And it goes plunk, and they feel those forces, both of them. The momentum of each one individually is changing, but not the momentum of the system as a...
So I have it a little bit sped up. It's really, you know, this is kind of rudimentary stuff. So he's talking about inside systems and closed systems and all that kind of crap. And to me, that's the wrong way to describe what energy is. Energy is the Descartesian thing, okay? Energy moves all the time. And clearly there's, you know, blocks of space, this room, where you can just say, let's just isolate the stuff that's already in the room and we won't worry about the stuff coming in or the stuff going out. We'll just call that equal. Certainly you could do that, but I just mean it sort of loses the feel for what you're really saying is that all the energy has an origin. Anything that's moving, there's something that moved it. The Earth's motion around the sun was created by a whole bunch of events. So it has a history. That energy, it has a historical, you know, it's been in the universe for billions of years, moving stuff in the universe.
The whole, and so this equals m1 plus m2 v prime. And so if we put in some numbers, suppose m1 equals 1 kilogram and v1 5 meters per second. Let m2 be 2 kilograms and let v2 be 3 meters per second.
Right, so he's just colliding two objects that are moving in the same direction. One's going a little faster than the other, and he's just saying you have to just add it up. Okay, you just add up what this one is doing and what this one is doing. You have a final mass and a final velocity, and that final mass and final velocity will be a ratio of that will always be inverse, that you'll always conserve the total amount. So all you're really going to do is change the total mass by combining the two objects, and you're going to combine their velocities to an average between the two and proportional to how much mass they brought into the experiment, and that'll give you your number.
And you see, since they're both in the same direction, momentum here is 5 plus 6 is 11. So this is 11. And this is 1 plus 2 is 3. So that is 3 times v1 prime. And so v1 prime is 11 meters per second. So the conservation of momentum tells you what the speed is after the collision. When we deal with collisions, the velocities of the objects before the collision are unprimed. You see here v1.
So he does this to his old videos, which is he edited them, and some of these edits you just say, oh, come on, it's a kind of a ridiculous point to be raising.
And you see here v2. Now the velocities after the collisions, by convention, are primed. You see here a v prime. Now if after the collision, object 1 and object 2 have a different velocity, we would call it v1 prime and v2 prime. Now in this case, we're dealing with an inelastic collision. So m1 and m2 are stuck together, they are merged, so it is sufficient to just call it v prime. You could have called it v1 prime, because v1 prime is the same as v2 prime, is the same as v prime. And during the next 4 minutes you will see.
Yeah, I would have done everything based on putting things before and after. So your initials would be subsets before the v, and afters would just be subsets after the v, but whatever.
That a few times do I call it v1 prime. I wish I really hadn't. It would be better if I had just used v prime. That is unique and sufficient.
I mean, it's unfortunate, really. Okay, we turn off the sound anyway. And they're not ads, you know, you can't skip them. So it's really hard ads that he shoves on his videos. He's allowing his corporate buddies, and it's more than one. So it's like, this is like a Ken Wheeler thing. You know, that's pretty desperately bad. Well, whatever. You know, and then the captioning always turns back on. It's just really is quite annoying, frankly. It's just not the way this railroad should be run.
Kinetic energy before the collision. And of course we can all calculate that. Kinetic energy before the collision.
So here he's just going to demonstrate that the kinetic energy changes because you've gone from small masses to one big mass, therefore increase the mass in a sense, and decrease. You've taken away the extra velocity you had in the smaller object moving fast, and so now you're going to have a velocity number that's lower, which means you're going to have less kinetic energy. So he's just basically pointing out that yes, experiments can violate conservation of kinetic energy, and it doesn't mean anything. Which means that kinetic energy doesn't mean anything, frankly. I don't know how anyone could take it seriously. If you don't have to conserve it, isn't it just nonsense?
1/2 m1 v1 squared plus 1/2 m2 v2 squared. 1/2 m1 v1 squared, 1/2 m2 v2 squared.
So, I mean, this is sort of a proof. I mean, he's basically just proving right here that kinetic energy is just nonsense. We should pay no attention to it because it isn't conserved, it isn't real physics, it isn't in the real universe, it's just imaginary fake little numbers. They might as well call this virtual photon or something, virtual energy. This is the virtual energy of the system. Doesn't mean anything, is silly, is stupid, and he's basically doing a mathematical proof, proving it's stupid, and yet they won't say, yeah, it's stupid, let's just forget about it. Let's just get rid of that and just pretend it never existed, and we'll do just fine without it.
How much is it? You can do that as well as I can. If you add that up, you'll find 21.5
I can do
joules.
math.
Trivial to stick in the numbers. Now I want to hear from you. What do you think the situation is with the kinetic energy after the collision? Don't look at the numbers. Just use your intuition. It may be wrong. That's okay. My intuition is often wrong. So there was a certain amount of kinetic energy. We had this collision, and I want you to tell me whether you think that the kinetic energy has perhaps increased or decreased, or maybe the kinetic energy hasn't changed. Who thinks the kinetic energy has not changed?
So, you know, obviously it's not conserved, so yes, nobody says yes.
Good for you.
Oops, a couple of people did.
Some parents even.
Oops, you made a mistake.
Who thinks the kinetic energy has decreased? Even better for you. Hey, there's a professor of physics there. I can't go wrong there. And who thinks the kinetic energy has increased? No one thinks that. Hey, it's amazing.
Well, that's because you already made it clear that the second answer was the right answer, so everybody's saying, oh, well, fuck, if I'm smart for guessing that it decreased, then I better not say it increased.
Let's take a look. Kinetic energy after the collision. That would be 1/2 m1 plus m2 times v prime squared. Would we agree? Let me write this at a different location. So this was the 21.5 joules. Well, you can do this as well as I can. We know what v1 prime is. That is 11/3.
He could have just did whatever that v prime squared. He could have just said m prime squared. So, I mean, m prime times v prime.
And you will find that this number equals 20.2 joules. So the kinetic energy went down. Now you may say, well, big deal, a little bit of kinetic energy, like 1.3 joules. Who cares about 1.3 joules? Well, it is a real big deal in physics, let me tell you.
So he says it's a real big deal in physics, let me tell you. But he won't make you any kind of rational argument about, well, why should it be a big deal? So again, this kind of goes back to my point that they don't understand it in the Descartesian sense. They're not understanding energy in the sense that energy keeps moving through the universe. It's the same clumps of energy moving through the universe, and that's what all the motion is created by, the same clumps of energy. A certain amount of energy is in the universe, and it's doing work. That doesn't fit with this idea, okay, that somehow you can make it disappear and then poof it back into existence somewhere else. So, you know, it just makes no sense. So he's sitting here arguing for a non-conservative energy reality. And you're just like, why are you doing that?
And I can make you appreciate that it is a real big deal by doing the following. I don't change the masses, but I just am going to change the direction of the impact. Here is M1, and here is M2.
This is big.
It's
This
really
is FiOS
bad.
2 gig.
No,
Switching
frankly,
out.
It's really bad. The ads have gotten worse and worse and worse, and it's just really bad.
I love what you've done.
The speeds remain the same, V1, and this is V2. No change in the numbers, except that they go now head on. What is the momentum of particle number 1? Well, that is mv.
So it's pretty annoying because he's going to consider these opposite directions as somehow positive and negative momentum, and they're really not positive and negative momentum. They're both real momentum, and if the two things do hit each other, you're going to know, like Descartes and Leibniz and Newton all speculated, that the energy's still in there. It's going to just require that it be, like if it's clay or something, it's going to get hot and it's going to spin or it's going to do something. So it's going to deform, it's going to crush. So if these are cars, they're going to crush. There's going to be a real evidence that the energy is going somewhere else, that it's doing other work. All right, it's not going to be some pretend it just disappeared, poof, it's gone. Oh, there's no momentum. There's going to be plenty of evidence that there's plenty of momentum.
1 times 5 is plus 5. Remember, this is the increasing direction of x. So the momentum is plus 5. What is the other one? That is 2 times 3. That is 6. Backwards. This is minus 6. So what is the total? The total momentum, if I give it the magnitude, equals minus 1. The magnitude is 1, of course, and the momentum, if I leave this off, we would call that minus 1, because it's a one-dimensional problem. The momentum before is in this direction. It's minus 1. So what now is v prime? They stick together. Here they are. And afterwards, I'm not even sure whether they go this way or this way. Yes, I am sure, because the momentum is in this direction. So I predict that v1 prime will be in this direction. And so this now equals m1 plus m2 times the new v1 prime. Well, m1 plus m2 is 1 plus 2 is 3 kilograms. And so you see that v1 prime equals minus 1/3 meters per second. So the whole system now goes off with 1/3 meters per second in this direction. The kinetic energy before has not changed. It was 21.5 joules, right? That is independent of how I collide them with each other. What now is the kinetic energy afterwards? This is a great tragedy, because now you get 1/2 the sum of the masses, which is 3, times this small number squared. Goes with v squared, right? And now there is only 0.17 joules left. Almost all kinetic energy has been destroyed. So what you see...
So, okay, so, I mean, does that make any sense? Can anybody make sense out of that? To say, okay, somehow you've destroyed the kinetic energy, that it's not a real thing, that you just made it poof out of existence, it didn't go anywhere, it didn't do anything, it just disappeared. Obviously it didn't. I mean, obviously the energy didn't. So kinetic energy doesn't seem a very good description of the reality. Now, I can't say much for how he describes the reality with momentum either, okay, but at least the point is made is that you have to account for where it goes. You can't just make the numbers disappear without explaining where they disappeared to.
See here in front of your eyes that kinetic energy can be destroyed, but momentum cannot be destroyed in the absence of external forces. Kinetic energy and momentum is a totally different thing.
So, yeah, and totally different how? How could they possibly be totally different? They're describing the same thing, the value of the motion. So they're giving you two different definitions of what the value of the motion is, what the quantity of the motion is. How does that make any sense? It doesn't make any sense to me. You can have two definitions of the same thing, and they can be different and divergent, and it doesn't matter. Of course it matters. I can't understand it as anything else. I mean, for somebody to say that the motion is not one thing, okay, it's made out of two components somehow. Somehow the motion is kinetic energy and its momentum. Well, how does it express that when all it is mass and velocity? And so, again, you're just saying mass and velocity equals. You're saying you square the velocity for whatever reason, for whatever rationale. There's no reasoning to it. There's no way velocity is a square of any kind, a geometry. It's a linear thing happening in one dimension. How do you convert that into a squareable geometry? So, again, I'm just honestly stating I can't make any sense out of it. If you can, I would appreciate you elucidating in some way how mass and velocity can be defined as two separately different things that are supposed to be both relevant somehow.
The momentum of the individual particles did change, but the net momentum did not change, but the kinetic energy was destroyed. I can destroy the kinetic energy completely if I want that. I can
Right, so he's basically conceding the point. It's all mush. He can make free energy. He can make it kinetic free energy. And we're supposed to believe it doesn't matter. So the gun does that, basically. I put two guns inside of each other. All right, the barrel of one gun inside the barrel of another gun, and then I put the same charge of one bullet in the barrel. I get 4 joules of energy. Somehow the bullet's charge only has 4 joules of energy. And then I put 2 bullets inside of a solid tube, and I just put 1 bullet charge. 1 bullet's a dummy, okay, just the mass, no charge. And then I fire that gun, I get 4,000 joules. That makes sense to you? Doesn't make any sense to me at all. How does the gunpowder know it's not supposed to produce any energy when the 2 guns are facing each other, but somehow it's supposed to produce an insane amount of energy when it's 2 bullets in the gun?
arrange a collision so that all kinetic energy has been removed. Suppose this particle has a mass 5 and the velocity is 1. This is my shorthand notation. And this particle has a mass 1, but it has a velocity 5. The momentum of this system is 0. Plus 5 in this direction, it is 5 in this direction. But you bet your life that
So that's the bullet hitting the gun.
this kinetic energy. After the collision, they hit each other. We agreed that they would stick. There was glue on it. Momentum afterwards must therefore still be 0. Internal forces don't matter no matter what happens. Kinetic.
So internal forces don't matter no matter what happens. I mean, obviously the fact that the interior forces, that is this object and this object, will become, you could argue, hot. They'll move, they'll deform, they'll do something. The energy will still be in them and it'll still be moving. And then it's going to go into the atmosphere eventually. It's going to leak out as heat or sound or photons or something.
Energy is 0. So the whole system collides, bing, and afterwards you have here the sum of the total masses, and it just stands still because I told you that they are going to stick together. I use glue.
Cole, he's
Again,
my miracle
amazing.
child.
Amazing.
So how does your miracle child get killed?
Yeah, because life sucks, bitch. That's how. Because it's stupid, okay? You're a dumb fucking bug, and bugs get cancer, and you should have known that ahead of time, that that was one of the chances you were taking with somebody else's welfare. Stupid cunt.
You have a car collision, and 2 cars hit each other, and I compare the situation just before the collision with just after the collision. Here are the 2 cars, and one has a speed in this direction, the other has a speed in this direction.
So it'd probably be better if you used a car and a truck or some other example just to prove that, yes, the momentum will move the collision in a direction. Okay, so that's sort of an indicator of more energy. So in a sense, that experiment can be done with the Newton's cradle, and Toady did that, and kind of demonstrated that it can have twice the energy come into, kinetic energy come into a collision, and twice the kinetic energy won't move the collision. So twice the momentum will move the collision, twice the kinetic energy won't move the collision. Kind of an indicator that, again, kinetic energy is just mush. It's just made up. It's not a real thing. It's CGI, it's just made up.
And they hit each other. And they stick together. It's a given. They go one big clump. So this is before. And I can give them some velocities. This is the speed of one, v1, and this is the speed of the other, v2. Afterwards, you see something like this. V prime. Just a wreck. The impact time is so short that the change in momentum due to friction with the road, that can be ignored. It's negligibly small. The cars hit. There is a huge internal force going on. One slams on the other, and the other.
So the friction is really with each other. That's the contact. The contact with the road is sort of irrelevant, blah, blah, blah. Yes.
Other slams on one. There is even fireworks. Metal scrapes over metal. friction, but that's internal friction, not friction with the road.
So we know it's internal, but it will leak to the external world. So we know that all of those things, little pieces will fly off, and very small pieces like electrons and protons, and they're going to be shattering a bunch of atoms, and little bits will fly off, and all kinds of ions, and all kinds of crap like that. So the energy is going to leak out of the system relatively quickly.
So momentum is approximately conserved if we can ignore the friction from the road during the impact, because the impact time is so short. So let here be car with mass m1, and here is the other car with
And
mass.
again, he's doing the conservation by claiming that there was no initial momentum. Because the two things were heading for each other, there was no net momentum. And it all depends on how you condition that example, in the sense that, again, if you give them disproportionate amounts of momentum, then you do have momentum before the collision, in the sense you have more momentum in one direction. But they sort of always try to engineer these examples to negate the momentum and pretend you're going from zero back to zero again. You're really not going to go back to zero.
SM2, and we'll make it a two-dimensional problem, because we've seen only one-dimensional problems now. Let's make it a two-dimensional problem. So this is the direction for this car, and let's say this is the direction in which the other car is going, velocity v2, and tragedy has it that this is the place where they're going to collide. In what direction and what...
So this is perfectly good vector analysis, and he's just going to do the simple addition of vectors, and there's lots of different ways you can do that. And so he could have just had them crash into each other, and he's basically going to say, well, after the collision I have momentum in a direction left over. So the initial momentum was the extra momentum that one object had more than the other object. Instead of saying the initial momentum is really two individual objects that have their own momentums, and you should total all the momentum no matter what direction it is, and then you should come up with the same answer. So it's the same truth, okay, whether you consider the objects individual objects with momentum regardless of direction. It's the same truth in the end, and all you're saying is yes, you have to come up with the bigger number at the end, because you're not going to pretend that these all cancel out. The ones going this way cancel out with the ones going that way. It's an unnecessary deception. There is no canceling out. It's all real energy, and you're just saying, yes, I'll account for it after the collision. So it is sort of annoying that they break the idea that energy doesn't care what direction it's going in. It doesn't pretend to say, well, because I'm moving this way, and somewhere in the universe something's going this way, therefore I don't have any energy. It's just kind of too silly.
What will be the speed after the collision? I only compare just the moment before the hit with just the moment after the hit. What comes later is a different story. When you have formed a wreck, clearly it's going to slide on the road, and then there is an external force, which is friction, which will slow it down. It's just during the impact, I claim, that to a reasonable approximation, momentum will have to be conserved. And so what is the momentum of
basically saying, yes, okay, it's not going to keep traveling. So you could just say, if we pretended it keeps traveling, we're just saying what's its initial velocity after the collision. So he's just saying, what's the velocity after the collision, right after the collision. Not after the wreck has slowed down and stopped, but right after the two collide, what's the velocity of the wreck?
this one? Well, this may be the momentum of this one. It may have a very small mass, small speed. And what is the momentum of this one? Well, this may be the momentum of number one, and this could be the momentum of number two. The net momentum is the vectorial sum of these two, which is this. That is P total.
So I like that little trick of just squaring it. Okay, that's the Pythagorean thing just done visually. It seems like visually answers the question pretty well. So yeah, if you make your vectors the length of the momentum, you can just get a visual idea of where the addition would place, well, the sum would place the new vector.
Of the system, that is never going to change. That's before and after the collision exactly the same. And therefore, if you know this angle theta, and you know P1 and you know P2, then you can calculate in what direction the objects are going to slide. But of course, you can also calculate then the velocity after the impact, because this total momentum must be the sum of the total of the two cars, the mass of the two cars, times v prime. And so you can calculate everything, and that's what the police is doing when they find wrecks on the road. They actually use the skidding tracks of the wreck to calculate v prime, and then they can try to reconstruct the situation as it was before the collision. Now, in all these cases, the objects stuck together. We've only
Now,
considered
how well they
cases
do
where they
that,
stick together.
Isn't really worth arguing. But anyway,
In which case, we call those in physics completely inelastic collisions. Now, next lecture, I will also deal with situations whereby, during the collision, the particles bounce off each other.
so they don't bounce. You're saying you're storing the energy, and then you're going to have a device that gives the energy back. So you can call that bouncing, but yes, it's more complicated than just bouncing because they're storage devices primarily.
In completely inelastic collision,
I mean, the bounce ones are like the Newton's cradle, where the steel ball bounces off the other steel ball, and there's no apparent capacity to store anything.
you always lose kinetic energy. Sometimes a little, as you see there. Sometimes a lot, as you see there.
So you're losing it because you're combining the masses and neutralizing the velocity to the lower number. So the default is you're just going to make sure the velocity is a lower velocity. The lower number is going to diminish the highest velocity. So the highest velocity is creating a squared term that's very high. You're going to lose that extra v, the higher v, because it's going to be averaged to a lower v. And that's the key point where, yes, you're going to have to lose energy because you've taken the fastest thing out of the equation and averaged it to a lower v number. So does it make sense to you? It makes sense to you to have an energy concept where you don't conserve the energy, where it's not a Descartesian universe, where somehow the energy just poofs into existence and then poofs out of existence. You don't need momentum to make sound. You don't need momentum to bend. You don't need momentum to make sparks. You don't need, it's like saying you don't need electricity to make sparks. It's that insensible. And I'm just saying, so I have to sit here and spend years arguing against a theory that's that insensible. That you're basically arguing that I don't need any wattage to make, sparks. When of course I do.
times everything, as you see there. Always in inelastic collisions do you lose kinetic energy.
Totals in before the end of the
Checkout
day.
is down.
Pooh.
Security or operational?
I don't know.
Is IT handling this?
Can we have in a collision an increase of kinetic energy?
So, I mean, it's really pitiful, right? I mean, you're just playing 10 minutes of a video, 4 commercials at least. I mean, just yuck. Yuck. Really ugly.
Energy? Well, it depends on how you define the word collision. The answer is yes. And in fact, I will show you an example and even do a demonstration. In the most simple case that I can think of, I have here a block which has a certain mass m. But there is an explosive inside. And all of a sudden it goes boom! It explodes.
So it's pretty poor to state it that way inside, because that would imply the block is going to blow up in lots of directions and make all kinds of mess in lots of directions, and that's not the experiment he's going to do. He's going to have energy in very specific directions.
Well, before, the speed is 0, and so the momentum is 0. And there comes the bang, and one piece flies in this direction with a certain velocity, v2 prime. This is m2. And another piece flies off in this direction with mass m1 with velocity v1 prime. Clearly, momentum must be conserved. This explosion is only internal forces. And so you can write down, if you call this the increasing direction of x, so this momentum is positive and this momentum is negative, the total...
So again, it's kind of silly, right, for somebody to say, look, the total momentum is 0, when no, you have momentum going this way and you have momentum going that way, and the total momentum isn't 0. I mean, both of those things are real capacities to hit something. If I put a dog or a cat and those things are cars that could run them over, you're not going to say zero momentum ran over the cat. I mean, come on, it's too stupid. It's real energy moving in two directions. There is no negative energy. So it's just kind of silly to say I'm going to make this a zero equation when it's really not a zero equation. You have two real momentums in two real directions, and you ought just to count them, add it up, and say what's the total momentum. Okay, it's this momentum plus this momentum. It's going to be some number like 15. And all you're saying is when I'm done, I have to, no matter what kind of M configurations I put here, I still have to end up with 15. So no matter how much I can pour cement into this, I'm going to change this V number. It's going to have to change to keep the number at 15. I'm always going to have the number 15 at the end. That's, to me, it's the way it should be explained. It's just wrong to say there's zero momentum in that system.
Momentum will never change. It's the same before as it is afterwards, so this must be...
So it should be 15 and 15. It shouldn't be 0 and 0.
M2 times V2 prime minus M1 times V1 prime. What happened with the kinetic energy? Well, kinetic energy has clearly increased. There was zero kinetic energy to start with. This one now has kinetic energy, and this one has kinetic energy.
So, again, isn't that sort of just baby talk? I just made free kinetic energy. We know it's not free, so what's the point of saying that? It didn't start with zero energy. We had a bunch of energy inside the explosive, blah, 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 blah.
Come from? Well, it was the chemical reaction of the explosion. Momentum, however, was conserved. See, momentum really doesn't care about these explosions. That's all internal forces. So be very careful. Never confuse momentum with energy.
Right. So, that's what they say. I'm just saying there's no way to get around momentum is energy in the universe. It's again, Galileo, Descartes, and Newton wouldn't have made any right predictions, wouldn't have said anything reasonable if they didn't understand that that's the source of momentum, is mass and velocity. Momentum is essential to understanding what energy is. He's saying that no, the only essential part is that little square we put on there. The mass and the velocity aren't the important thing, right? The momentum. No, the important thing is the squared velocity. That's the only thing you should pay attention to. I mean, it doesn't make any sense. It's ridiculously irrational and illogical. Come on. The square is the important part. The M and the V isn't? Come on.
Energy can change or cannot change, can increase or decrease or remain the same, kinetic energy. But if there are no external forces on the system, momentum is always conserved.
So he's saying it. He's making it explicit. Okay, even though momentum isn't energy, we're going to conserve it, whatever it is. Okay, so whatever it is, you have to conserve the momentum. So whatever that means. And you're going to conserve the square. And then you're just going to put the square on the momentum. And so I guess that's how you rationalize this nonsense. But there's no way to make sense of saying that the essential thing is kinetic energy. That's real energy, but we're not going to conserve it. That's ridiculous. Clearly the essential energy, the real energy, is in fact conserved in the universe. So why are we pretending it must be momentum, because that's the one you conserve, is the MV. You have to conserve the MV. You don't conserve the kinetic energy.
And this is what I can show you. I have a demonstration set up on this air track, and we do it on an air track, so there is a minimum of friction. And we're going to push two cars together.
So this is all redundant and pretty simple, but it has the famous quote in it, so we might as well play the entire context of the famous quote. So he's already stated pretty clearly you have to conserve momentum. So he's already stated it more than once. It's in the title of the video. Okay, so it should be understood that's what he's saying quite explicitly. Now other people are going to try to say he doesn't mean what he's saying. I think he means it.
And we hold them together with a spring. The spring is like the explosion, like the dynamite that can push these apart. So here is one car on the air track, then there is a spring, and there's another car. Let this mass be M1 and this mass be M2. And
all right, so the experiment being done in the case of Ian Gosling is the same experiment. You're just saying M2 is, monstrous. It's the Empire State Building. It's not going to move. So M2 is too heavy to move at all. And you're just basically saying, what's the spring going to do to M1? And the argument is it has to conserve the momentum. So if I make M1 100 pounds, it's going to move at a velocity. If I make it 50 pounds, it has to move at twice the velocity because it has to conserve the momentum.
This surface is nearly frictionless. And I hold them together with a string so that I can pull the spring in. So this spring is compressed. And the whole system is at rest. V equals 0.
Right, and now he's doing this whole string thing merely because he has to release the energy at the same time for both objects or it's not going to work. If the spring has more time or to work on one side or the other side, then it's going to change how much energy it puts in one direction or another direction. So to make it a pure explosion, he has to make it, he has to take all the biases out of giving this one any resistance to motion is the key. I mean, this one too, in his case, just because it's not infinitely heavy.
There is potential energy in that spring. I take a burner and I burn away this thread. This is the situation before. Momentum before is 0. Total momentum afterwards will also be 0. It's identical to what I did there. And so this object will fly in this direction, and this object will fly in that direction. And you already can tell what the ratio of the velocities will be, because you will see that v2 prime divided by v1 prime, you see it right there, equals m1 divided by m2. And so I will make some predictions about the speed of these two objects. The largest mass, by the way, would get the smallest velocity. And the smallest mass would get the largest velocity, the largest speed.
That's just divvying up the energy from the spring's release between the two objects is the simple principle. The same pressure will be applied, and then it's, you know, it's just off to the races based on you getting hit with that much momentum. So they're both going to get hit with momentum, and they're going to react to that same amount of momentum by the half mass object moving twice the velocity as the twice as heavy object.
What you see in here are really speeds. We don't have the information on the direction anymore. How do we measure the speed? Well, we actually measure the time for the cars to move 10 centimeters. Each car has a little metal plate which is 10 centimeters long, and it blanks out a light-emitting diode. And the moment that the light-emitting diode is occulted, the timer starts, and the moment that the light-emitting diode emerges again, the timer stops. So that's the way we will measure the time for each car to move by 10 centimeters. The first experiment that I will be doing, M1, is 244 plus or minus 1 gram, and M2 is also 244 plus or minus 1 gram. In other words, the uncertainty in the masses is something like 0.4%. That's just part of life.
We'll zoom through this.
The time that it takes for object number 1 to go 10 centimeters is obviously 10 divided by v1, which is the velocity that we want to compare them with. Now, the 10 centimeters is really only known to an accuracy of about 1 millimeter. So that is an uncertainty of 1% in my timing, in my velocity. So this is a 1% uncertainty. So if we measure the...
Spends a lot of time on this uncertainty stuff and then starts talking about how the diode works. And so again, this is all kind of not, it's superfluous to the real subject.
Times that object number 1 and object number 2 will go through his timing device, a measurement of 10 centimeters, you would expect the time to be the same, to within roughly 1 plus 0.5, say 1.5%. There is how...
I was down to talk to my doctor about Rebelsis.
Ask your healthcare provider about Rebelsis today.
When we were a motorized bicycle company, they said, you'll never be more than that.
Ugh, Jesus Christ. Suck. Who even buys shit from these stupid fucking commercials? They're just so irritating. I don't even know why.
The following.
They
Here is
work.
the light-emitting diode, and here is that metal plate that I mentioned to you, which comes over this diode, occults the diode, and says start the timer, and then the other end, of course, moves off, and then the timer stops. That criterion for on and off for one diode may not be exactly the same as for the other. Here is one system, one car will fly in this direction, and here's another system, and the car will fly in that direction. And that's not so easy to evaluate unless you do a lot of experiments. So I would roughly guess, I'm always on the conservative side, that this may add an uncertainty in the criterion of the diode of another millimeter. And so effectively, I really don't know any better than 2 millimeters. what the 10 centimeters is. So I would say we really have to allow here for 2% plus 0.4%. So I would predict that the times of these two cars will be the same to within roughly 5%. That would be my prediction. So we're going to write down here the times, and then we're going to measure them. So time 1 and time 2. And we will see whether these two numbers are the same within the uncertainty of our measurements. Here's the air track. Have to turn on the airflow. Oh, let me tell, for those of you, for the parents in my audience who haven't seen this one, this is a marvelous device. It is a track which is well constructed so that these cars fit beautifully on this V-shaped track. And then we blow air out of this track, which lifts these cars up so that they float. And so we can move them in horizontal direction with extremely little friction. There is no metal touching metal. The only friction you have is the air drag. That you can never avoid.
Right, so the only downside, as I've sort of discovered, is that it is creating more energy in your system. So your whole system is floating on a cushion of added energy. And if your carts tilt at all, they will use that energy as essentially an exhaust and give your objects more or less velocity. So if they, if the cart for some reason rises or lowers, it will add energy in a direction. So that's a downside.
When you go through the air with a car, there is wind, the same wind that you feel when you drive your bicycle. But it's very little, and that's why these experiments are done on these air tracks. These are not cheap, by the way, these air tracks. They're very expensive.
Yeah, so that one's probably $10,000 because it's MIT and they don't mind spending the money.
Well, you pay $25,000 tuition, so you might as well get something for it, right?
So that's kind of interesting because when I was going to maybe go to MIT, it was $17,000, something like that. Between 15 and 20, I remember the number, and LSU was half as much. It was only $7,000 a year, so it's a big difference. So that's why I chose the cheaper college that I never went to. But anyway, just a little history. I almost went to MIT. Almost.
So I hope that these timers are on. They are. And now we have here one car. And notice how frictionless it goes when I touch it. Very nice. Almost frictionless. And here we have another one. And they have equal mass to within 1 gram. And there is a spring between them. Some of you may be able to see it.
So there's 2 springs between them, actually. So, but yes, that shouldn't make any difference. Shouldn't make any difference.
And I'm going to attach now that string to hold them together. And so I put potential energy in the spring by pushing them together. And they're lined up now here. They have no momentum.
So you could see a little bit of a flaw in that, right, would be the fact that, let's say if I did the experiment that way, that there would be a tendency for the 2 carts to tilt up a little bit, right? So the stronger I made that pressure, the more likely it is the carts are going to start lifting. And as they lift, that's going to mean that the air is going to come out the 2 sides, which means it's going to deter, actually, their ability to fly away from each other equally. But anyway, I don't see any of that being a problem, but I'm just saying that's the liability of the air track.
Timer's not on. Has to be reset. Thank you. You're now both 0. Yeah, you sure? Okay. So now I'm going to burn off that wire. The momentum of each one of those cars will change. One will go in this direction, the other one in this direction. Kinetic energy will increase. That's the potential energy from the spring. But the momentum of the system as a whole, after I burn the wire, will remain 0.
So again, it's just kind of silly to say the momentum is 0 when the 2 carts are flying away in 2 directions. I just say, come on, that's just physics being silly. It's a wrong way to describe this system of energy. The understanding is that I would have to have momentum to compress the spring. So I have to use momentum to compress the spring. That's the initial momentum that went into the system. The initial momentum is the compression momentum, the pressure, the weight I have to apply to compress the spring. And now I'm going to release that, and I have to conserve that initial momentum. So if the cart was going 20 miles an hour into the other cart that I held, and the 2 cars compressed the spring with that pressure, I have to get that pressure back.
Ready for this? Make me happy. What do you see? You're going to make me unhappy? I better walk around. I can't wait. 220. Oh, fantastic. Absolutely fantastic. 223, 219 milliseconds. That is well within the uncertainties. What was the number? 219? 219 milliseconds and 223 milliseconds. If I repeat the experiment and I make the string shorter, I will get different times. I can never predict the times, because if I make the spring more squeezed, then obviously I will have more potential energy, and so the speeds of the cars will be higher. But the times will be the same within the uncertainty of the measurements.
More importantly, you'll conserve the momentum, so you'll have to account for it. So like I said, in Ian's experiment, clearly the momentum is not being conserved. The lighter object, the half as light object, isn't leaving with twice the velocity, so you haven't conserved the momentum, and he's saying he doesn't have to explain that. Okay, and I'm saying, yeah, you do. How did it fail to get how did the momentum fail to get into the object?
So I can never predict the time. Now we're going to do an experiment whereby...
I mean, nowhere in this whole video does Professor Lewin say the word inertia and say, oh, this cart can't move because of inertia. This cart can't move because of inertia. There's no argument that inertia is getting in the way somewhere.
I'm going to make M2 twice the mass. M2 is 488 plus or minus 1 gram. Now that's going to be interesting, because now you really begin to test the conservation of momentum. The momentum before is 0. I burn the wire, momentum afterwards is also 0. But the velocities, oh, I erase this, v2 prime divided by v1 prime.
So here's the famous quote that I've been using, and why not? Because it's a statement by conventional physics. This is the statement. The dissenters, those arguing with me, all seem perfectly comfortable saying what Professor Lewin's going to say now is wrong. But they won't say he's wrong. They won't comment on his videos saying he's wrong. They won't make videos pointing out that he's wrong. They'll just pretend that attacking me is somehow relevant when it's conventional physics that believes it.
Equals m1 divided by m2. And so twice the mass will get half the speed. And so now you're going to see that one car will go twice as slow as the other. That's the only way that nature can conserve momentum. Nature has no choice. Nature can deal with kinetic energy one way or another, but it cannot finagle momentum. So it must...
So, yeah, let's just do it one more time for the fun of it.
Now you're going to see that one car will go twice as slow as the other. That's the only way that nature can conserve momentum. Nature has no choice. Nature can deal with kinetic energy one way or another, but it cannot finagle momentum. So it must give the more massive car half the speed than it gives the other car. And
so same thing as saying it must give the lighter car twice the speed. The half is massive. So again, in Ian's proven experiment, his proof, he's saying he has proven that's not a rule. Okay, the lighter object doesn't go. The half as mass object in the same pressure, in the same force circumstance, doesn't go with twice the velocity, and the momentum is not conserved. Clearly his statement.
So we're going to redo this experiment now with a car here which is twice the mass, and this one is one's mass. So this is the 244, and the one on your right is the 488. So I have to bring them together again.
I don't even know why he has to explain that to anybody. It's obviously twice as much cart, but whatever. He has to explain which one's heavier. You know, it's a little ridiculous.
With a string. So I do the work now. I always do the work here in 26100. I do the work. I squeeze these springs. I get paid for that, by the way. And that's potential energy that goes...
So it would be nice if these were the same springs, but they're obviously not. So in this case, the only one that has a spring is the big thing, has the big loopy spring. That's it. So there's no, there's only one spring in this one, as I remember.
Goes into the spring. Where it is. Momentum is 0. Kinetic energy.
So the little cart has the big floppy spring on it, and so it's just the one spring. Oh no, there's a little one on this one. Okay, so it's the same configuration, but the different cart has this cart's big spring.
Is 0. I have to 0 the timers.
Now you would assume they tied all these strings to be the same length, like around the same object to make them all the same length. So they should be creating very similar compressions. No. But the answer is no, it's a little bit off. So this one was obviously has a little bit more energy than the other spring's compression. So not much, but it is a little.
Oh, and I would like...
Oh, it's a little less. Yeah, the time is longer, so the times are slower. So it produces a little less energy than the other experiment did.
like to make a prediction. I would like to see, we'll measure T1, and then we'll measure T2, and then we get a number, and we get a number, and if we multiply this number by 2.00, then I would like to get this number, within the uncertainties of the measurements. There is always an uncertainty in any measurement that you do. All right? Make sure that, are the timer 0? Okay, there we go. What do you see? Ah, 406, 193. Whew! On the button!
So it really wasn't. It was really almost 5%, so he really had to use all of his margin of error. But anyway.
406 and 193. 0.406, is that what you see? Yeah? And 0.193. Now I don't even need my calculator to multiply this by 2. I can even do that by heart.
It's kind of funny.
9, 3.
So, whoops. Yeah, so he had to correct his mistake. So it's about 2.5% instead of the 5%. So, yeah, but it's a lot more.
I'm Ron Finley, also known as the Gangster Gardener. This garden was...
Fuck you. Gangsters. Fuck. I ain't buying that. Fuck you, AT&T, for being annoying. Fuck you, whatever you are. Temptations. Yeah. Fuck you too.
6. Close enough. The two are in excellent agreement within the 2.5% uncertainty in each measurement. So, you see, that's exactly how you can demonstrate the conservation of momentum.
All right, so it's a real thing, conservation of momentum. You can't just diminish it and say, it doesn't mean anything. I can do an experiment. I don't have to conserve the momentum. I can prove kinetic energy. I can prove guns don't fire bullets. No, you can't. You can't do that. You can't say something that's completely contrary to all the other experimental evidence and claim it's a proof and you've done it and we don't need to worry about it anymore and we all should be convinced because you made a bullet roll out of the gun, somehow.
They picked up kinetic energy, but after the wire was burned, the momentum remained 0.
All right, so now he's going to go to center of mass, which is more about oscillators and resonance and all of that stuff. So I don't think we need to play all that. Because it's really not the same subject. All right, so maybe we'll do a little bit of chat and see if anybody has anything to say, and then I'll go find some other video, I guess. Visual give me no other choice. Let's see, what do we got? 7. Oh, it's not too good. 8. Okay, well, it's still not too good. Not good enough. We need more participation. It is a sad place, this world. I mean, the Wolfram guy does this every week, where he does a chat talk thing. Now, he mostly gets on one subject and just talks it to death and doesn't do all that much interacting with the chat, but it is some opportunity, I guess, if you can catch his attention, which is pretty unlikely. Now, I've tried to encourage him to engage in conversation, and maybe I'll try some more. But he doesn't get many views either, and he's kind of, he's in that pop section where people know who he is and all that kind of crap. I mean, he certainly knows all of the gatekeepers, and he certainly could get, he certainly has an in to, you know, the chain of popular viewership, and yet, you know, his live chats don't get much participation. I mean, frankly, he had like 10 likes, you know, after 10 hours. And, you know, that's almost as bad as my videos, frankly. So, you know, it's just not me that is being dissed by the internet. And I just think it's sad that there isn't more interest in physics. I mean, clearly the interest in physics is mostly just kids trying to pass tests in school. There's not that much interest otherwise in real physics, let's just say. Obviously, there's plenty of people who are going out and looking at free energy videos and singularity videos and whatever wormhole videos and all that of crap science. Watching Veritasium bury himself in cement. I didn't even watch that video, so I have no idea what he actually does. But this whole, I mean, it's just such stunty bullshit. I just don't know how science-minded people don't find that obnoxious, that you're turning science into a show. Ugh, fuck. Anyway, so, yeah, I mean, well, Adam asked kind of an obvious question. What's the difference between the spring experiment shooting straight up versus shooting sideways? Well, theoretically, there shouldn't be any difference, okay? Because both objects are going to be experiencing the same environment. Now, the clear truth is that if you actually roll objects with a spring, you'll find that the object going twice the fast will go 4 times the distance. Now, you shouldn't assume that's because it has more energy, because it won't do that in 4 times the time. And gravity is what's really controlling the friction. And so the friction won't be linear, the same amount over the same period of time. So you're not absorbing. The ground isn't taking the energy at the same rate. So it takes energy from slow things. You could sort of understand something rolling slowly. It's taking the energy more per inch than if something's rolling very fast. And I could illustrate that with the scale. If I roll something over a scale, you can understand the faster I roll it, the less of the weight will be registered by the scale. And I could theoretically go fast enough where the scale wouldn't even know I drove over it. I could actually roll a car fast enough over this scale that the scale would just go, you know, little tiny deflection, even though it's a 4-ton car that flew over it. So, but they're identical experiments. You're putting 2 things in the same environment. So yes, going up into gravity, the same rule applies. The fast thing has a huge advantage in terms of how high it will go. But if you forget about that illusion and just recognize you're just talking about a velocity at liftoff, there's no difference. The half mass is getting half as much resistance to gravity. Gravity is half the resistance to the full mass. And so obviously the half mass should go twice as fast into the gravity because there's only half the resistance to its motion, its velocity, its acceleration. So in a sense, the 2 experiments, doesn't matter which way I point them, because both the heavy object and the light object are facing the same obstacles, technically. So if I shoot them sideways, I should expect the twice as fast object to roll 4 times further. If I shoot them up into gravity, I should expect the one going twice as fast to go 4 times higher. And if it doesn't go 4 times higher, it can only be because it's not going twice as fast. So, I don't know. It's sort of a trivial question, but okay. Alright, so that's all we got from you people. Gee, I was hoping for better, but if not, I just have to do this shit. I really don't want to do it, but... Alright, so we have to find a video here that is of some, you know, this is a search and not finding too much, frankly. Alright, this is a conservation of momentum, but really they're talking about putting the gun on a roller and then having the thing, so the gun is being allowed to move. It's not really a spring against a brick wall. What we really want is a spring up against a brick wall. That would be the real experiment we're looking for. And unfortunately, nobody does that experiment. Momentum study with springs and half balls. Alright, so let's see what that is. Doesn't sound good, but we'll see what it is. I don't know, it doesn't look quite right, right? Doesn't look quite right. Oh, there's no sound, and it's a very wide video. So that's really quite useless, right? I mean, that is... what the fuck was that? So why would somebody even publish this piece of shit? Spring balls. Half spring balls. So it's really just a Newton's cradle thing, so very uninteresting. So that was a disappointment. Alright. Let's see. Momentum of 2 spring carts lab. Alright, well, let's just try it for the hell of it. Of course, they have to have ads on their poorly viewed videos. I got 10 cents this month. We don't need the music, thank you. I don't know if they're going to talk. Apparently not. No. Alright, track, 2 carts, blah blah blah. It doesn't look like we're going to get anywhere here, so we'll just see what the procedure is. Make sure the track, yeah, okay. Who cares, blah blah blah. Each centimeter point, blah 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 blah. Just get to it, thank you. Thank you, get to it, thank you. Okay, here we go. Now that was very exciting. Alright, so they're just doing the same thing Professor Lewin just did. Heavier cart, lighter cart. Momentum has to be conserved, so nothing new to see here, really. Let's see. Alright, now this one looks kind of inelastic trials. Okay, so they made them stick together with some kind of weird shit. Yeah, see. Oh, that's Velcro, okay. So we know that works too, that you just have to conserve the momentum, so you're just really making, 2 objects into one object, and you have to share both the mass gets added, and then you have to apportion the velocity based on who brought it. What mass brought the velocity will tell you how much momentum it was, and you're just really just adding the momentums. Spreading the velocity over the bigger mass. So you're taking the total velocity, the average velocity, and you're spreading it over the bigger total mass. Alright. So the argument is just this simple, that you always have to look, if you don't conserve the momentum, you've got a problem. So that's the lesson to be learned. So all these experiments conserve the momentum, there's no problem, blah blah blah. And so obviously people who create an experiment where you don't conserve the momentum, that means you have a problem, and you have to explain why you didn't conserve the momentum, where the fuck it went. Spring conference, I don't know what that is. Okay, let's see. The wait is over. The Peel Student President Council is excited to bring you the spring conference. I don't know, it sounds like some video just to spread some sort of shit. And this year, we're interested in Sparky, whatever, I don't know, Christmas fun. I don't know what the fuck that is. The hell with it. Alright, football player talking about momentum probably doesn't mean much. And baseball player talking about momentum probably doesn't mean much. Alright, so this is again just the same spring moving off the mass thing. Let's see. Really, the known velocity about this one, explosion problem. Yeah, so same thing. Alright. Same thing again. Same thing again. Potential energy of a spring. Well, we have vectors in different directions. That's not going to help us any, I don't think. Let's see. Connected to a wall. Well, it's connected to a wall, so at least we have that. So let's see what we get. Khan Academy. Okay.
Welcome back. So we have this green spring here, and let's see, there's a wall here. So it's connected to the wall. And let's say that this is where the spring is naturally. So if I were not to push on the spring, it would stretch all the way out here. But in this situation, I've pushed on the spring, so it has a displacement of x to the left. And we'll just worry about magnitudes. We won't worry too much about direction. So what I want to do is think a little bit. Well, first I want to graph how much force I've applied at different points as I compress the spring, and then I want to use that graph to maybe figure out how much work we did in.
All right, so this is probably just going to be the math of kinetic energy, which doesn't mean anything, okay? Because they're not none of the quantities are actually measured, so they just say so, and they don't prove so. So it really doesn't add up to anything at all.
Compressing the spring. So let's look at. And I know I'm compressing to the left. Maybe I should compress to the right so that you can. We're just worried about the magnitude of the x-axis. So let's draw a little graph here. So let's make my y-axis, my x-axis.
So far, not so good.
And so this axis is how much I've compressed it.
All right, so again, this is the same pointless comparison. This doesn't mean anything. You can't multiply these two numbers because they're basically the same number. The force equals how much the spring compresses. Yeah, duh. Why would I multiply those two numbers? Yeah, no good reason at all. So let's zoom through this and see.
This is how much force I have to apply. So when the spring was initially all the way out here. To compress it a little bit, how much force do I have to apply? Well, this was its natural state, right? And we know from, Hooke's law told us that the restorative force, the restorative force, I'll write a little r down here, the restorative force is equal to negative k, where k is the spring constant, times the displacement, right? That's the restorative force. So that's the force that the spring applies to whoever's pushing on it. The force to compress it is just the same thing, but it's going...
Right, so you have to have the constant. You have to have the k number, then you'll know how stiff the spring is, and then you know how many joules per millimeter it can produce. The k is the whole thing right here. This x is almost like, duh.
In the same direction as the x. If I'm moving the spring, if I'm compressing the spring to the left, then the force I'm applying is also to the left. So I'll call that the force of compression. The force of compression is going to be equal to k times x.
Yeah, and we know that we already know that the x part is completely proportional to the weight. So we know that as you increase the weight, which is the momentum, you increase, linearly how much you compress. So twice the weight, twice the compression, 3 times the weight, 3 times the compression, 4 times the weight, 4 times the compression. That's how this scale actually works. Okay, that's why it does work, is that it is linearly connected. Okay, the spring proportionally moves based on how much weight there is, how much mass and velocity there is, and it really is about masses and velocities. I can drop things onto the scale and it will tell me the instantaneous total amount of energy that thing, weight, momentum, it produces. It will measure momentum. Scales are momentum measurers. Analog scales, spring scales.
And when the spring is compressed and not accelerating in either direction, the force of compression is going to be equal to the restorative force. So what I want to do here is plot the force of compression with respect to x. And I should have drawn it the other way, but I think you understand that x is increasing to the left in my example, right?
Through some of this horse shit. Who cares? Blah blah blah.
Okay. Really and realize you didn't apply 0 and then apply k force. You keep applying a little bit more force every time you compress the spring a little bit.
Yeah. So it's a nice straight line.
The slope of this graph
very exciting.
Is the distance.
Not
right?
really.
So the work is just going to be the sum of all of these.
All right. So
we know the slope is k, so this height is going to be x naught times k. 5 meters.
So he's obviously not doing anything. He's not doing anything. He's not comparing this to anything real in the world. He's just saying the bullet has 2,000 joules. Well, says you it does. Yeah. Where did you measure it? Oh, that's right. You didn't. No, that was useless. This looks pretty close to useless. What the hell is this? Slope builds momentum heading into sprout. Okay, he's building momentum. It doesn't look like he's building momentum. Looks kind of gay, actually, but whatever. Let's see. Collisions, conservation of momentum. No, that doesn't look like anything. Vertical spring. So this is just hanging the weights and just pointing out that, oh, it does have it against a wall. Well, let's see. We'll see if there's any hope here. It says vertical, but there was a picture of horizontal, so...
Let's say you've got a mass connected to a spring and the mass is sitting on a frictionless surface. If the mass is sitting at a point where the spring is just at the spring's natural length, the mass isn't going to go anywhere, because when the spring is at its natural length, it is content with its place in the universe. It neither pushes nor pulls. It has no spring energy. This is like me most days in the summer. So we call this point where the spring neither pushes nor pulls the spring's natural length. And for a mass on a horizontal spring, this is going to be also the equilibrium position. And what we mean by equilibrium position is the point where the net force on the mass is 0. So for a mass on a horizontal spring, the equilibrium position is at the point where the spring is at its natural length, because the spring wouldn't be pushing to the right or the left. And if you just put the mass there at that point, it would just stay there forever at rest. That'd be boring. So let's say we pull the mass to the right, a distance d. If we do this, we give this spring potential energy. And if we release the mass from rest while this spring has spring potential energy, the spring's going to pull the mass back to the left, and that mass is going to move through the equilibrium position with some speed. And we can figure out what that speed is just by using conservation of energy, and it's not that hard. The potential energy the spring would start with would be 1/2 k.
Right. So again, it's the same bullshit of squaring. So, and you could do it with momentum. So again, just understand that it's just as valid to take this square off and get rid of this 1/2 and just say kd. Just as valid. You'll get an answer that'll be completely proportional. So if you shovel the mass, you'll get a proportionally doubled answer. It'll give you the same answers, okay? It won't give you different answers, because there's only one object in the equation, frankly, and there's only one amount of force. And so it doesn't matter whether you say there's 300 or 600, it just matters that you understand that it's going to be half as much for half the compression.
Spring constant times d, the amount the spring's been stretched.
Now we'll jump ahead, see if he gets to anything real.
Here, you don't just have a spring force, you've got a gravitational force. And you don't just have spring energy and kinetic energy. Think about it. This mass is moving up and down. You've got changes in gravitational potential energy. So why don't we have to take into account the gravitational potential energy?
Well, because you're going to give it back and it's going to just move back and forth. That's why you don't. Or whatever. Alright, so the time, the equilibrium position is this place. Well, whatever all that means, we'll see what
essentially our new equilibrium position. In other words, that's the point where the net force on the mass would be 0. But this time, that's...
So he's just talking about the oscillator as it travels through equilibrium and goes back and forth, back and forth, back and forth. So oscillators don't really help us in this circumstance. So that's all he's really obsessed with is the oscillator. Okay, so not useful. Spring momentum, no conservation there. So all these are lacking the word conservation now, apparently. So not useful. Momentum music, momentum crew. Oh, this looks like a great crew. Like, egads. Dancing and prancing. Let's see. Build momentum with strings. Now, this is, they're really getting poor now. We're really getting not very relevant. Spring wishes. That's way off. More dancing stuff. More dancing and prancing. Okay, so forget it. We're way off the subject. So we'll go back to the top, which was all redundant, really. Spring, bouncing off spring, spring off spring, spring off the spring, pushing block and friction, which is not very useful. So Van Briesen's pretty good, but this doesn't have really much to do with the energy stored in the spring either. So this is just from the Professor Lewin video I just played. Let's see. Knowledge, test your knowledge of momentum. Build bullet striking a block. So this is just the ballistic pendulum, and it's basically again another conservation of momentum argument. But it really doesn't do us any good because there's no springs involved. Momentum energy spring. No. Okay, so this is the two carts. Same, no experiment, just more illustrations. Alright, well, we'll just give up. And then we'll see if anybody has anything to say in the chat. And then I'll just get the hell out of here because none of this is going to help us. Let's see, a momentum mix. They used to give you the option to just go to the playlist, and you can't do that anymore. That's really annoying. Well, let's see what happens. They'll start playing the video, and I don't want to play the video necessarily.
Always go with your gut.
I like that. Let's go with our gut.
Ah, fuck you. All right, let's see what these are. Can pro baseball player hit a tennis serve? Well, it's pretty fast. Yeah, 120 miles an hour. No, 131 they say. It's pretty fast. Let's see. Can I hit a pro pitcher with random objects? Who cares about that? Can 4 grown men beat a high school baseball team? Let's see. Pro athlete versus internet troll. Who wins? I don't know. These are all kind of joke videos, I guess. Clickbaity kind of crap. So, fuck it. Can a homemade bat hit a baseball 100 miles per hour? I saw somebody who made some sort of, they just waste like a whole year to make a mechanical robot bat that goes like at super explosive speed or something and has like dynamite in it to see how fast they can hit a baseball. I mean, what the fuck? Well, that was unfortunate. Yeah, so not a good playlist. Alright, maximum spring compression between colliding carts. So again, that we've already done. Same old springs, but no springs against walls. Alright, Professor Lewin rationalizing some sort of mush right next to a Ken Wheeler video. Oh, hilarious. Anyway, using springs. So this is obviously the same bullshit. So, alright. Spring momentum. Let's see if this playlist has any hope. They didn't play it. There's only one video in the playlist. Oh, you're so clever. Thank you so fucking much. Alright, this is, whatever that, Arbor Scientific. So, I already played this video, smashing burning paper. Already played this video with, the fact that momentum is just momentum. Frankly, rotational inertia, there's no extra inertia, there's just masses moving a speed. You just figure out how fast the mass is moving, you know how much momentum it takes, you know how much energy required to create that momentum. So it doesn't tell us anything either. This is just the same old gun spring recoil thing. So instead of banging things into each other, they're just basically changing the shape of the cart. It's just really just hitting two carts. It's really just putting the spring between two carts and pretending, so it's the same exact configuration, really. There's just no difference. Alright, so we'll leave it there, and we'll see if anybody has anything to chat about. If not, we'll just get out of here. Making my effort, and it's just, you just can't find the video. Alright, Tim, I can't link YouTube videos strangely. Yes, I know. That's they should give me the choice to allow certain people to post links. You should be able to have linkable people and unlinkable people. Something. But no, there's nothing. But anyway, so just email it, please. Okay. But wanted to share the best visualization I've seen for the argument that the momentum is conserved, not KE, in a collision. Yes, well, email it to me, and then I will play it in a future video, blah, blah, blah. Probably the folks that are interested in physics aren't watching YouTube. Why would that be, exactly? I'm just saying, there's physics lectures on YouTube. I mean, it's really fantastic. I mean, you can watch MIT lectures. I mean, Stanford, all these colleges. I mean, it's an insanely valuable resource. Why wouldn't smart people want to do that? Anyway, how can a collision conserve momentum but not KE? Channel physics explained. I have to go. Oh, this is the title. Okay, how can a collision conserve momentum, but not KE. Well, good. It gets to the point anyway, right? I mean, that's the statement being made here. It does seem ludicrous. All right, so we'll pop that into the search. All right, here we go. Bingo.
It's hard to believe Mint's new family plan is just $15 a month per person. So I've asked my wife and plan member
to fuck you too.
I'm going to show you how to make this animation. We're going to remake the animation parts of it. I'm gonna skip some steps, but I'm going to go over everything. And this comes from the question: how is it possible that momentum can be conserved but not kinetic energy? So let's run this animation and then we'll talk about that. So here I have a yellow ball.
This looks a little scary, frankly. It doesn't look like any normal spring, but whatever.
Colliding with this other thing I made.
Oh, thank you. Oh, okay, so they're going to say the kinetic energy is caught up in this oscillation or some kind of crap like that. I don't know. So momentum works, but kinetic energy is, look, it's storing a whole bunch of kinetic energy in this thing, but this thing doesn't. Somehow these atoms are made out of different stuff than these atoms. I don't think I'm going to like this video.
I mean, when I made that, I was just like visually attracted to it, and I love it. So let's talk about
I think it's silly, okay? It's silly to think this thing is made out of different matter than this thing is made out of. They have to be made out of matter. Matter is mass, and then you give it velocity, and the mass is always the same shit. It's just the weight of atoms.
It would be confusing, and then we'll come back over to the code, and we're going to make this code, and I will give you the code. You will have the code, and you can do whatever you want with the code.
Why, Tim, did you think this video is a great explanation? Wow. Amazing. This is a steaming piece of shit. He's going to give us code. How exciting.
In your class, or not used in your class. Okay, so paper time. So suppose I have two objects that are colliding. So I have object A, it's moving towards B, and B's at rest, just for fun. B's at rest. And so it has an initial momentum PA1, meaning initial. And then it collides. That's my symbol for later, sometime later. And then they both move. Who cares? It's something. I mean, I care. We all care. But they're both moving. If we define momentum as mass times velocity, and if we have no external forces on the system.
So again, this is pretty superficial. He should establish that he's going to hit the one that has the momentum is going to force the other one to share some portion of its momentum, and you don't have any momentum in any opposite directions.
Then the change in momentum of the system has to be 0, so the momentum before it has to be the momentum afterwards, and we can write that as the following equation.
Very exciting.
MAVA1, mass, velocity, B, all that stuff. Okay, well, if kinetic energy is 1/2 mv squared, and they both depend on mass and velocity, how can the kinetic energy not also be conserved? So should not 1/2 MAVA1 squared scalar plus 1/2 MBVB1 squared is not necessarily equal to MA.
Yeah, and you see the little scalar word he used, right? So we know the momentum is in one direction. The MV is in one direction. So why is the kinetic energy a scalar when it's made out of a thing that has a vector? So it's made out of a thing that's a clear vector, the momentum, MV, and yet they say it's magically a scalar, which means it's going in any direction. It's not going in any direction. It's going in exactly the same direction as the momentum. It can't go in any other direction. It has to go in the same fucking direction as the fucking momentum. So it's such a cheaty, cruddy way to create this fake, phony language. You know, I mean, it's just, you know, Jesus rose him from the dead or something. I mean, it's just kind of, you know, what the hell is this conversation about? How exactly did he do that rising thing?
VA2 squared plus 1/2 MBVB2 squared. And I'll go ahead and tell you the short answer, and that's why I made that animation. If B has some internal structure, like I replaced B with two masses connected by a spring, then the center of mass of this will have the same momentum as that, but it may not have the same kinetic energy because the energy...
And it won't have the same momentum. So if you make your little oscillator, it's going to use the momentum to create those oscillations. So it will not conserve the momentum in the sense that you will now trap the momentum in the oscillator. So this is back to the physics girl nonsense, that somehow you make the heavier train, okay, going the slower speed by, you know, hitting a 5-ton train into a 5-ton train, making a 10-ton train, and somehow you lost half the kinetic energy, but you're going to argue that you have conserved the momentum. So you still have all your momentum, and yet you made sound, and you bent metal, and you made sparks, and you did all this other crap. You can't do both. So this is a lie. He can draw it. He can make a simulation of this lie where I use the momentum to move the objects, and then I also use the momentum to create squishy, wobbly things. No, you can't do both. The energy can't do both things. It can't create an oscillation inside this object and give it momentum in a direction. It can't do both.
Internal energy takes away some of that energy. And I think it's really easier to see in the animation. So let's just jump back to the animation.
Fake animation.
And build this code. So let me go over the important parts of the code.
All right, I don't think we're doing coding here, Tim. So that's probably not going to happen. But anyway, let's do it real quick.
Groove rides are all about getting out of our head and into the music.
Commercials everywhere.
It's important to understand
364.
what's going on. If I have
364 views. I mean, how much is he making on these commercials?
Balls, A and B, and this one doesn't have any internal structure. How do I make a collision? Well, one way, the way that I want to do it, is to say, well, if these two balls overlap, so let's imagine that here's A, and it's overlapping with B a little bit. In that case, I'm going to say there's a force, this is of A pushing on B, and then there's a force push of B pushing back on A that's proportional to this overlap. And we can say F A on B. I can calculate this vector from here to there. I'll call that R. And then I can say F is going to be equal to, if they overlap, negative K R. I think I can say it like that. So the more they overlap, the greater the force they push apart, and it doesn't even matter. As long as these two forces are equal and opposite, then momentum will be conserved. And that's not too difficult to do. I mean, you have to have some if statements in there.
Yeah, well, they're equal masses and all this kind of crap. So he's going to get into the whole coding thing. So, well, yeah, we're really not going to do that. I mean, my code is so much smarter than this monstrous pile of mush. So forget it. We're not doing this. Yeah, this isn't that interesting. Yeah, see, this is all, we're not doing all that crap. So, Tim, you disappoint. Just a fact. I mean, I was hoping for something a little better than that. I think the Professor Lewin video was a much better statement about the requirement to conserve momentum and the fact that there is no requirement to conserve kinetic energy. He said it pretty clearly. All right. Only a moderator can share links in the chat section. Oh, okay. Well, I can make people moderators. If you throw a ball upwards, I mean, I could probably trust Tim. Tim seems a trustable character. Oh, they don't let me do it here? Oh, maybe they let me do it over here. Let's see if they do. Add as moderator. So there you go. I'm giving you some power, Tim. You look like a responsible person, just cares about, interacting constructively. So we'll give you your chance. And really all you're supposed to do is post links from now on. Okay, you don't have to do any moderating. All right. What the hell is this? Can review and remove chat messages and hide or put users in timeout. Can manage blocked words and change chat modes in live, and also has capability of standard moderator. Well, I think we'll just make you a standard moderator for safety. Okay. We don't want you blowing up the channel. Okay, let's see. Where the hell was he? I can link YouTube videos strangely, but what the hell is that? Now we got a huge jump in things here. Where the hell was I? Alright, Tim says, only over, okay. Let's see, if you throw a ball upwards, okay, this is the retard, without pushing on the earth, then you're what, free floating in space, or what, you jumped in the air and then you're going to throw the ball? I mean, what are you talking about? The ball reaches a certain altitude, then stops. It has a velocity relative to the earth, and it has a velocity relative to you. So which one are you talking about? Which means the earth gains the ball's momentum. Whatever. Fuck you. Too silly. The point is they're both in the same circumstance. You're throwing two balls. One weighs twice as much as the other. How does the earth know I'm going to take all the energy from one and I'm not going to take any energy from the other? How does the explosion in the gun know I'm supposed to give 2,000 joules of energy to the bullet, and I'm only supposed to give 2 to the gun. Is mass a scalar? Fuck you. There's no scalars. There's no vectors. It's just bullshit, okay? It's all... Look, energy is always a vector. Always. Even a little piece of heat is a vector. It's moving in a direction. Energy moves in directions. Straight line directions. That's what I would argue. Now, you want to believe it's waves? I don't care, really. But the idea is the edge of the wave is always going in a direction. At any one point on the wave, you could say it has a perpendicular direction, okay, to the wave surface. And that's its direction. Okay, it's a vector. When mass is moving, does it make it a vector? Yes, it's always a vector. Always, always a one-dimensional vector. All right, now it's wrong to say that, because you can have momentums in 2 different vectors. But the point is that the 2 separate vectors don't interact. So if I throw something this way and gravity pushes it this way, those 2 momentums are in fact separate. Alright. The video I suggested was that it seemed to be the best visualization for the argument. I don't know. I don't see how it's possibly the best visualization of anything. Sorry. It was a piece of crap. He's making up a fake ability to transfer momentum and to use it twice. He's going to use the momentum twice. You can't use momentum twice. I mean, you have to go sequentially. You can't use it twice at the same time. It has to go from place to place in an order. And it can't stay in an oscillator and then also do some other kind of work. Alright. What the hell happened? Alright. We did this. Next, the ball will fall towards the earth, which means the exact moment before it hits the earth, the ball regains its momentum. I'm sorry, this is too silly. So you're just about... I'm right on the verge of blocking you, because this is too silly. Alright, which means the exact moment before it hits the earth, the ball regains its momentum. That's just too silly. But now the earth is at the same moment, has doubled the ball's current momentum. We're not doing word problems in the chat, so if you can't link to a video, you can't link to something, then fuck off. Really, this is just horse shit. Because the earth had to stop the ball and then gravitate it. Whatever. The gravity's just a stream. If you're in the stream, it's going to push you. You have a boat that's big, you get pushed by a lot of the stream. You have a boat that's small, you get pushed by a small amount of stream. This is how the spring behaves, but inverse. Well, whatever. This is all bullshit. You're saying that somehow the spring, more energy goes into the ground when I put a half mass on the spring. Well, why doesn't that happen to the gun? Why doesn't that happen to all these other things? It doesn't happen to all those other things, so why is it happening in this, as you're claiming? Alright. And with electromagnetism rather than gravity. Well, fuck you again. Like I said, I'm just going to have to just get rid of you. Did you see Dr. No, there's no Dr. Castro that means anything. It's a new video. What do you mean he doesn't have any videos? Just kidding. But he did just publish a bunch of papers for NASA measuring particle energy in space using scintillators. I don't know if that's new published or old published. But obviously that's just how they detect muons. I mean, it's not news. It's not interesting. You know, who cares? What does it have to do with any fundamental physics? Nothing. Anyway, fuck this. It's not an interesting thinger. Peter Thing. Somebody thinks you're a somebody somehow too. So I don't know whether you're just a Dr. Castro troll or what. But whatever. Thanks for the moderator access. I won't let it get to my head and abuse the power. Yeah, very good. I've been reading his paper on who cares? RxCTV, where nobody else reads papers. I mean, I went there, you know. I mean, people had a paper published 6 years ago and it's got 4 downloads. I mean, what's the point? And downloads means 4 people who just read it. No, I mean, just clicked on it. Doesn't even mean they read it. But what did you find interesting in his papers? I didn't find any new science in anything. I didn't think his papers even suggested anything. He's also working on pulsed radiation sources now and fundamental interactions. His papers are, somebody should go read Dr. Castro's papers because, now I remember, they're the most convoluted pile of crap you could ever read. So if you know anything about all that color, quantum physics crap and all that kind of shit, it's full of all that kind of shit. So it's all just full of standard model wacky physics, Higgs boson, all that kind of bullshit. There's absolutely nothing to do with anything real. Okay, now I'm just giving you advice, Peter. I'm going to block you if you're just going to be a fanboy for some anonymous coward Castro guy he says nothing, he doesn't do anything, he doesn't produce any content, he now and then comments on a De Hilster video. He's not relevant, okay? I don't know why you think he's relevant, but he's not relevant. He's not an expert on kinetic energy. He's not an expert on anything. He doesn't say anything. He doesn't make any arguments. You can go fuck yourself if you want to keep mentioning him. All right, his thesis or what he works on at NASA. He's not even, how do you even have evidence he still works at NASA? I mean, how do you, what do you think? You think the guy chatting on De Hilster's board actually has a job? Jesus, how do you even know it's the same guy? I mean, this is just such silliness. Please explain his relevance. Would you please explain why you think this individual is relevant? What has he said anywhere that makes sense to you? So besides being a defender of relativity theory, what exactly has he said that makes him at all interesting? Well, you've got to know the Department of Energy is not a scientific thing, right? That's a corporation thing, okay? The Department of Energy finds ways of making the worst financial investments in energy possible, okay? So it tries to find ways to make little shysters rich. People who want to nail your solar panels on your roof. It tries to find ways to make them richer. Okay, it doesn't try to do anything brilliant. So, I mean, yes, Tesla obviously went insane, okay? There's no, I mean, people ought to just concede that there was a point, I don't know, when he hit whatever, 65 or something, where Tesla literally just went batshit crazy. The neutron energy spectrum, yeah, there's no neutron energy spectrum, so this is all just, look, okay, Peter, this is your last warning. You say something relevant to a subject I could find any kind of interesting, or you just fuck off, okay? That's it. This is your last warning. You mentioned one more fucking thing about this Castro asshole, and I'm blocking you. I've asked you to say how he's relevant. He's not relevant. He's spoken no meaningful words on the internet. There's nowhere to find a meaningful statement made by him. It's impossible to find. Okay, we're blocking you. I'm just done with this horse shit. I've already explained why he's irrelevant. You're obviously just a troll. Okay, got it. Fuck off. God, people are just such scummy little creatures. See, the trolls think they can make a thing out of this. Because I blocked the Castro character because he would say nothing, right? I mean, he just kept saying, I'll debate you, but he wouldn't debate me. Right? And then he asked the question, what's the subject, right? So after 10 years of doing this, he asked me what the subject is. And that was it, okay? He's willing to debate me, and he doesn't know what the subject is. I mean, that was just too ludicrous. And so now they're going to pretend that this Castro guy has some sort of relevance, that he could make a video, that he could do Skype, that he could say something on the internet, when it's obvious he doesn't say anything on the internet. He has no internet presence. He doesn't have one. He doesn't make videos. He doesn't produce any interactive content. He's obviously not very good at debating because he doesn't do it anywhere except in chats. So why the fuck would I debate somebody who only debates in chats? But they're trying to make it a thing, so that's why they create this fake account for this whatever Peter thing is. I don't know what that is, right? Yes, trolls. That's all there are. Yes, just a very high percentage of the human race is a troll. They don't have any competence. They don't have any ability to do anything decent. They're just the shoplifters, you know. It's like everybody's become a petty thief. And whack job liberals have decided to glorify the petty thieves. Oh, little lies are good, and little thieving is good, and you know, poor people have to steal stuff because they can't do any work, because they have to play video games all day because they all have Asperger's. I can't post a link, but the video title is Physics, Test Your Knowledge. Bullet striking block. So we know this doesn't mean anything. I mean, bullet striking block. They can just make up the numbers, so it's not going to show us anything. And I've already done this. I've already shown Professor Lewin doing the ballistic pendulum. It doesn't. And we already know conservation of momentum is a real thing. So how do you think this is going to illustrate why a half mass is required to go twice the velocity? Do you really think that's what it's going to do? Because I'm going to contend, no, it's not going to do that. It's going to fail to do what you're claiming it's going to do. Shit. I mean, if you're going to give me links to real stuff. Okay, so this is again, I like Michael Van Briesen, but you know, this is going to be a full of no useful information video. Veritasium with his, you know, putting bullets into blocks shot in the air. I think he did that one. Thanks to everyone. Oh yeah, it's 9 years ago. All right. The fact that you have to conserve momentum is not, frankly, in dispute within conventional physics. So the point I'm making is that Brozo and all of the haters of me seem to have as a consensus the belief that they can violate conservation of momentum, and it's not a problem. So that's
metric units, but they're not used very much anymore. Usually we convert everything into newtons and joules, but let's work the problem out using these.
So I've obviously already watch this video, so that's why it linked, you know, to the middle of the video. So let's go watch the beginning again, see what we're going to get.
Firing a bullet towards a block. The block is sitting on a frictionless horizontal plane. The block is attached to a spring, and as the bullet hits the block, it doesn't go through the block, it gets embedded in the block and pushes the block into the spring compresses.
So we know this is only an ideal thing, right? There's no such thing as creating this substance that can collect all the energy in the right direction. So we know some of the momentum is going to go to splitting wood in other directions. The wood is going to do stuff, and it's going to get hot. And so we know we're going to lose not a trivial amount of the momentum of the bullet is going to be lost. I mean, frankly, you're not going to measure it with this spring because the direction isn't going to stay consistent with the bullet's direction, because it's really hard to collect the energy in just one direction from something going as fast as a bullet. It's really hard to do it. It's hard to keep the energy in the right direction because it wants to scatter.
A total of 10 centimeters before the block gets pushed back. So the questions are, first of all, what is the maximum potential energy in the spring when it's fully compressed? What is the velocity of the block right after the bullet hits the block? And what is the initial velocity of the bullet to make the block compress the spring 10 centimeters? So notice we have some interesting units on the board. We have the mass of the bullet in grams, the mass of the block in grams, the compression in centimeters, and the spring constant in terms of dynes per centimeter, 50,000 dynes per 0.5 centimeters, which would be 100,000 dynes per centimeter. Notice that a dyne is 1 times 10 to the minus 5th newtons, or a newton is 100,000 dynes. And also we have the units of erg on the board. 1 erg is 1 times 10 to the minus...
So this is really not going to help much, right? I mean, he's basically just saying the K is going to be somewhere around 1 point, plus 1 or minus. I think it has to be always below 1, a K value. But it's going to be something like 0.9 or 0.8 or 0.7, but whatever. Instead of that, he just had to say all this rubbish about this 10 to the minus 9 Newton crap and all the rest of this shit that doesn't help at all.
7 joules, an erg is a dyne times centimeters. So notice that these are still metric units, but they're not used very much anymore. Usually we convert everything into newtons and joules. But let's work the problem out using these old units to see how they work.
No.
The reason why they used to have those units is because back in the old days, we didn't have calculators, and so therefore it was more difficult to convert things with the scientific notation, so they used units like these. Let's go ahead and see how they work. First of all, the maximum potential energy of the spring. Okay, when the spring is fully compressed, we can say that the potential energy is equal to 1/2 kx squared. Now notice 50,000 dynes.
So again, he's just doing the calculation in kinetic energy terms. He's going to come up with a number that is in kinetic energy terms. They're never going to prove it. They'll never show that's what it actually has. And again, you can do exactly the same mass and just get rid of the half and get rid of the square and just measure it by momentum, and you'll conserve the momentum. So it's just bullshit. No point. I thought, oh, okay, that's where I changed it. All right, so let's go back to this and then just go back again so I don't lose where I was. All right, I'll put this stupid chat thing back. So thank you, but that wasn't very useful. I mean, it's really just mush. I mean, I could play Professor Lewin doing it, and the fudginess of the outcome results are just that. It's just fudge. Just grotesque estimates, So he did it in 2 different ways, I think, to figure out the momentum of the bullet. And he did get 2, the answers really weren't that close. They were with like 20% difference. So, this mathematical analysis is only so useful because you can't create any of these perfect circumstances. This frictionless surface and this idea that you can capture the bullet and you capture all of its energy in just the one direction and you don't lose any of it to any other direction is just kind of bullshit. Probably the better way to do it is to do the cylinder thing. So take a water tank. How would you get the bullet into the water, though, is the tricky part. Yeah, so never mind. Just because you could, I suppose if you shot the bullet into a water tank, into a deep water tank, something deep, so it takes a long time for the bullet's energy to be absorbed by the water, then all the directions would count because it would raise the water. So you can just measure how much the water rises with a cylinder, and that would tell you how much energy, how much water the bullet displaced. You have to think about that. Because maybe it just give you the volume of the bullet. Yeah. Yeah, it's hard to say how much energy because you'd have to create air bubbles or something. Yeah, no, I don't know if it'll work. Never mind. I guess the temperature one you could use. So you shoot the bullet into the water and then measure how much the total increase in the temperature of the water is. And that might tell you. But yeah, the temperature of the bullet's going to be, it's not going to tell you just the momentum of the bullet. It's going to tell you also that the bullet's hot from leaving the gun. So some of the momentum is in the form of heat. So the bullet's already hot, which is going to ruin those results too. Anyway, we really don't have to use bullets. We can use much slower things to do these experiments. So it just should be made a point that guns do conserve momentum. Okay, so the gun's recoil is the same energy as the bullet's momentum. You know, they both have the same momentum. And it's kinetic energy that goes all wacky. Alright, well, maybe it's time for the 2-minute warning and such. Some people are not very interesting, frankly. Yeah, you're not very good at this. Anyway, 7. See, there's always 7. The number goes down. I mean, that's really bad. So, yeah, it's pretty hard to get anything done when there's only so few participants. So, whatever. First half of the video is good enough. It's like a regular one of my videos, and people just don't bother watching the second half because, yeah, there's not much interaction happening. Unfortunately. If anybody can find somebody who's willing to talk about physics, to make these arguments, in some way that has continuity, where I get to ask questions and he has to answer, not just I get to ask questions and I have to answer, it goes both ways, that kind of thing. So, I'd be interested. So email me if you know of anyone capable of having a, they have to be knowledgeable. I mean, they have to have seen, Professor Lewin style videos. They have to have some kind of knowledge of the experiments that exist. And then maybe they can explain where the momentum goes and how you can not conserve momentum. Alright, so looks like we're done. So, till the next time, and such, and so forth, and whatnot. I might as well check real quick just to see if the Brozo or the Iron has made a new video. Nothing there. Pretty sure Brozo. So Brozo was going to ASAP is going to show us the billiard ball experiment done perfectly. It comes out with 1.4. Perfect destruction of momentum. Yeah. No, we're not going to see that video, I guess. Nope. No sign of it. 10 days later, or whatever it is, 2 weeks later. Alright. So anyway, till the next time. Yep, nothing else there. Okay. So, that will be all, folks. Blah, 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 blah.